All right, this is maximum, minimum, increasing, decreasing practice. This is for sure going to be on the AP exam somewhere in more than one places, I would expect. So do make sure you understand what is going on here. Now, looking at your first question, you need to know where this particular function has a critical point. So we know f of x has a critical point when f prime at x equals 0. So we look at f prime at x, that's going to be 1/2 plus cosine x. And then if we set this equal to 0 and solve, we have 0 equals 1/2 plus cosine x. And so we're looking for what values around that unit circle that's listed over here as our multiple choice that's going to give us negative 1/2, and that's going to be answer choice A. Okay, for number 2, the function has a relative maximum when, and so we know that g of x has a relative maximum max when, and we know g of x changes from increasing to decreasing, and so if we put that in terms of our first derivative, we're going to say when g prime of x changes from positive to negative. Okay, so let's look and see where does that happen at. So over here we need to find g prime at x. G prime at x is going to be 12x squared minus 6x. We do need to set this equal to 0 and solve, because finding those critical points, our relative mids and maxes, occur around those critical points. So in factoring this, it looks like I have a common factor, so I'm going to factor out 6x. And so I have a 2x minus 1 left. And solving for x, notice that we get x can be 0 or x can be 1/2. Now, a lot of places tell you to do a number line, but we focus a lot on graphs, and so I would just graph this derivative. We know we have a critical point here, which is going to be an x-intercept, and also over here at 1/2. So I would just do a quick little sketch of my derivative. This is the graph of g prime at x, and I would look to see, well, where does g prime at x change from positive to negative, which is going to be from above to below the x-axis. So that's going to happen right here at 0. So for number 2, your answer is B. How many critical points do we have? So to find a critical point, that's going to be where your derivative of the function equals 0. And so what we can do here, let's do our derivative, and we're going to have to do the product rule with the chain rule. So we're going to have f prime at x equals, and we have the first times the derivative of the second, and the derivative of the second is going to be 4 times x plus 4 cubed times the derivative of the inside, okay, plus, and then it's going to be the second, so we have x plus 4 to the fourth times the derivative of the first. And the derivative of the first, we need our chain rule, so we're going to have 3 times x minus 1 squared times the derivative of the inside. And so let's clean this up a little bit and see what we can do with it. So I'm going to set this equal to 0, of course, to find our critical point. And really rearranging here, I have 4 times x minus 1 cubed times x plus 4 to the third, plus, and again simplifying a lot of this other stuff, I'm going to have 3 times x plus 4 to the fourth times x minus 1 squared. And so I would go through with this and I would look for those common factors. I would not multiply this out. There's no need for that. Inside the parentheses, notice I have an x minus 1 cubed and an x minus 1 squared. So an x minus 1 to the second would be a common factor. So I have x minus 1 to the second. And then I would also look and see that x plus 4 is in both terms. So you will choose the one with the smaller exponent. So x plus 4 cubed. So there's our GCF. So now I would go back and we write in, well, what's left over if I factor these out of both terms? Well, if I do that, I have 4. And notice I should have 1 of my x minus 1's left, plus, and then we have 3. And it looks like we're going to have an x plus 4 left. Now you can continue to solve this, but notice it's not saying what are the critical points, it's just saying how many critical points. Well, I'm going to get 1 critical point from here, I'm going to get 1 from here, and 1 from here. So it looks like I'm going to have 3 critical points. Okay, moving on. Here, for what value of x? Well, y'all just heard the bell. So for what value of x do we have a relative minimum? So again, relative minimum, f has a relative minimum. So I would go ahead and write that out. Has a relative min when, and that's when f of x goes from decreasing to increasing, which for my derivative means f prime of x changes from, we're doing minimum, so from negative to positive. Okay, so first thing, we need to find those critical points because the critical points will be what we classify as relative min or maxes. And so we now need to do our derivative and set it equal to 0. So I'm going to say 0 equals, and if I do my derivative here, I'm going to say, well, we have the first times the derivative of the second, which is just 1, plus the second times the derivative of the first, so x minus 1, times the derivative of the first. So the derivative of the first, we need the chain rule, so we're going to have 2 times x plus 1 raised to the first times the derivative of the inside. So let's clean this up a bit. So I have 0 equals, and we have an x plus 1 all squared here. And then over here, let's see, we have, looks like we're going to have 2 times x minus 1 times x plus 1. And again, I would not multiply any of this out until I just had to. I would look for a common factor here. And notice x plus 1 is in both, so I would factor out an x plus 1. I don't think there's anything else left, so I would have my equals 0. On the inside, I have x plus 1 left from the first term, plus, and then from the second, I have 2 times x minus 1. And so if we continue on here, we have 0 equals x plus 1 times, let's see, this is an x plus 2x, so 3x. And let's see, what else will we have? Positive 1, negative 2, so minus 1. And so again, keep in mind, we are looking for a relative minimum. And y'all, if we multiplied this out, we would have a parabola. So I would go ahead and sketch my parabola. Notice that when x equals negative 1, or when x equals 1/3, I cross the x-axis, so I have negative 1. I have 1/3, so I have a parabola sitting here doing something like this. And relative min, we need from negative to positive, so from below to above. So it looks like we go from a below to above right here at 1/3. So my answer is C. Right? Here they give us, let's see, the graph of the derivative. So we notice this is f prime. Always look to see which graph you're given, because you could be given the original, the first, or second derivative. And so I want to know, based on this, where does f have a relative maximum? And again, f has a relative max when f prime at x, because relative max, that means f is increasing and then changes to decreasing. So f prime of x changes from a positive to a negative. Okay, so where do we find that? From a positive to a negative. Oh, so let's look. From above to below is going to be right there. So my answer is D. All right, so we need to find the value of K so that we have a relative minimum at 2. Well, a relative minimum, excuse me, a relative minimum, well, that's just a classified critical point. So really we need to find the critical point. And it's saying really that critical point is 2. So we need to go through our derivative. So f prime at x is going to equal, well, x squared, derivative of that's 2x. Now this is a little weird. I would rewrite that. So I have k times x to the negative 1. Oh, y'all can't read that. But it is to the negative 1. So that's going to be negative 1 times k. So minus k x, and negative 1 minus 1 is negative 2. Okay, so let's see what that looks like. F prime at x equals 2x minus k over x squared. And then notice what it tells us. We have a relative minimum at x equals 2. So for my derivative, that means when x is 2, then my whole f prime is 0, because the critical point means that f prime equals 0, and it's already telling us that we have that critical point or that relative minimum at 2. So I can say 0 equals negative 2 times 2 minus k over 2 squared. And now we have an equation that we can solve for k. We're going to end up adding 2 over, or 2 times 2, so I have 4 equals negative k over 4. And so let's multiply both sides by 4 to undo that division. So I have 16 equals negative k. So let's see. Did I miss a sign? Why did I put a negative here? No, I missed a sign. So I don't know where that negative came from. So if I subtracted that over, that's negative. So k is 16. Goodness, folks. All right, so that answer is E. I'll take a neck on that one. All right, so for number 8, we're back to doing derivatives with charts. And so based on this table, we have all these different functions. Which of these functions must have a relative maximum? Relative maximum. So I would stop there and think, okay, relative maximum means that I did what with my derivative? Relative max happens when, let's see, my derivative, relative max happens when f prime, or g prime, or h prime in this case, changes from positive to negative. So let's see what's going on here. All right, so glancing through here, we're just looking from -3 to 3, so we're looking over the entire interval. And I'm looking to see where I change signs. Well, notice f of x here. All of these derivative values are positive, so that tells me that the original function is only increasing. Well, let's look at g of x. We're looking for positive to a negative. Well, the only thing I see for g of x is changing from a negative to a positive, so that's right the opposite. Now I know it's not going to be some of these answer choices through here based on that. H of x, I'm looking for a positive value to a negative value. There's one. So it looks like we might have h being the only function that happens on. So your answer choice is D. Right, number 9, minimum value of the derivative of this occurs. Well, again, we are looking for the minimum value. Oh wait, this one's worded weird. Minimum value of the derivative. Minimum value of the derivative. I think we're going to have to go talk to the second derivative. It's all the first derivative rules, but as far as minimum, maximum, relative min, relative max, but we're applying it to the first derivative, which means we need to look at the characteristics of the second derivative. Good gravy. All right, so we have f prime at x. What is that going to look like? We're going to have 15 x to the 4th plus 20 x cubed. I need the minimum value of this. That's what this is asking for, is the minimum value here. Well, that's different. It's different, but not really. So let's look at the second derivative, because we can apply everything we already know, but we apply it to the second derivative to get the minimum value of the first derivative. So let's look. 4 times 15, I believe that's 60 x cubed. Hey, we got a cubic function here, plus, and that's going to be 60x squared. Well, that worked out kind of nice. And we really need to find a 0. That's the critical point of the first derivative. It looks like we can factor out 60x squared. And we're going to have an x plus 1 left. So all of that ugly gobbledygook really ended up saying that I have some critical points for the first derivative function, which are really just possible points of inflection for the first, is going to be x equals 0 or x equals -1. Well, again, instead of doing a number line analysis, I would graph this. We know what the graph of cubics look like, the little curly Q's, and my leading coefficient's positive. So let's see, we have -1, we have 0, and my cubic function is going to go up, and it's going to do something. Oh, but y'all, it doesn't really cross because I can't cross back. Oh, this is doubled, so we're really just going to bounce and go back up. Oh, let's draw a better graph of that. I know it's bouncing because of that squared. When we talked about radii, we talked about bounces. Here's a bounce. We've got that squared term in my factored. So let's see if we can't do this again. So it's really going to come up, and then it's going to bounce and then go back up. That's my second derivative graph. And so if I want to know a minimum value, well, the minimum value for the derivative, well, we're still looking for minimum value is going to occur from when my derivative goes from a negative to a positive, which is still going to be right here at -1. So my answer is D. Right? Number 10. Number 10, we have this. Notice they give us a lot of characteristics, and it's talking about the graph increasing or decreasing. Well, if we're talking about increasing or decreasing, then that means I need to go look at my derivative, because f of x is increasing when f prime of x is positive, and f of x is decreasing when f prime at x is negative or less than 0. So we need to look at the derivative here. So we have f prime at x equals 3x squared plus 12. All right, well, that's kind of weird looking. If we set this equal to 0, we get 0 equals 3x squared plus 12. It looks like we have a GCF of 3 and only 3. That gives me x squared plus 4. Well, if I set this equal to 0, well, my goodness, what's going to happen with that? Well, if I set this equal to 0, well, 3 can't equal 0 because it's too busy being 3. X squared plus 4, if I set that equal to 0 and try to solve, I get x squared equals -4. Well, when I take the square root of a negative, I get imaginary numbers, and we're not dealing with those. So this isn't crossing the x-axis. Well, that's kind of strange. Well, what's going to happen with this? Let's look at this form here, or even back up here. That's really a parabola, isn't it? And let's see, where in the world, what's going to happen for this? I just don't see where that would ever be decreasing. This is always positive, isn't it? Because if we start graphing this, we have 3x squared plus 12. So plus 12, that means this parabola is going to be moved way up here, plus 12, and then 3 Well, that's kind of strange. Nowhere is that derivative going to be negative. It's not below. Notice here, and that 3, well, that 3 should have made it skinnier than that, but I don't care. This is not negative anywhere. Notice that my parabola is up here. So if we're not ever negative, well, that means that we're always positive. So the answer is going to be B. Wow, that's going to be B, because here, notice, this is not negative. This is the graph of the derivative. Don't be tempted to grab this over here, this side over here, and say, but it's decreasing. The derivative's decreasing, but that derivative, all of this is still above the x-axis, so it is still positive. That's a strange one. Good problem. Okay, for number 11, same idea. Where is f of x increasing? So we need to find where f prime, so this is going to be where f prime of x is positive. Now this one's going to be a little different, I think. Let's see, f x, I would rewrite this so that I have 1 minus x squared. That's going to be to the negative 1. So f prime of x is going to be negative times 1 minus x squared to the negative 2 times the derivative of the inside. Don't forget that. And the derivative of the inside is negative 2x. So let's see what that ends up becoming. Let's simplify this up a bit. So f prime at x equals, we've got a negative times that negative, so I have a positive 2x over 1 minus x squared squared. That is so strange. Because thinking about the graph of that, we're not going to know what the graph is just off the top of our heads for this. But let's think about, we still need 0. Need to set this equal to 0. And I have 2x over 1 minus x squared all squared. Well, the only way a fraction can be equal to 0 is if the numerator equals 0. So I'm going to come over here and say, well, that means that 2x would have to equal 0. So x equals 0. So there's a critical point. And then we also need to talk about where this derivative would be undefined because we have strange stuff there. Or let's talk about what would be vertical asymptotes. Well, on the inside here, if I set 1 minus x squared, if I set that equal to 0, then I'm going to add x squared over. I'm going to take the square root of both sides. So plus or minus 1 equals x. So again, I've got some strange things going on here with this function, but I know I have some important points that I need to go look at. So on a number line, we're going to try to make this easy if we can. I know I have negative 1, I have 0, and I have a positive 1. So I need to know what's going on our x-axis right here. And let's see, I could go ahead and draw in the y-axis, except for we're not really going to know a lot of y values. Well, let's pick some values and plug in. But notice this denominator is squared. So that means no matter what I put in the top, the bottom part will always be positive. So we don't even really have to worry about what we get in the denominator. So let's look on the other side of negative 1. If we chose negative 2 and we plug negative 2 in right here, well, that's going to give me 2 times negative 2, which is negative 4. So I have a negative, but in the denominator it's going to stay positive. So on this side of negative 1, I have negative. So I know that my function is down here somewhere. So I'm going to say negative right here. Well, what about between negative 1 and 0? Well, between negative 1 and 0, let's see, over here I picked negative 2. Over here, let's pick negative 1/2. And again, I know the denominator, no matter what, is going to have to be positive because it's squared. If I plug in negative 1 on the top, negative 1/2 times 2 is still a negative, so a negative divided by a positive. So we're still negative here. So my derivative is staying negative here. So it's really doing something down here, and it'll just touch that, but it continues. It's still doing something like that. So let's see, what else? What about on the other side of 0? Well, on the other side of 0, we have a negative here. So let's see, on the other side, let's choose a positive 1/2. Well, if I plug in a positive 1/2, well, then that's going to give me on top a positive, denominator positive, so I have positive going on here. And then on the other side of 1/2, let's pick a 2. And again, if I plug into my derivative just to see what the sign is, well, that sign is going to still be positive. So we're positive over here. So now remember, at 1 it was 0, so it's doing something funky over here, but we're still above the x-axis. So let's look at our answer choices. All the way to the left of negative 1, we were negative. So if my derivative is negative, my function is decreasing, but I'm looking for increasing. So I know, well, I know we don't increase everywhere because I had some negative values. B, negative 1 to infinity, well, that's over here, and I was negative, so it can't be that. It looks like there's a type O here. I think that should be parentheses there. So from 0 to 1, we were above the x-axis. The derivative was above. And then 1 to infinity, it was also above. So my answer choice is C. Okay, on to the next. So for question 12, same kind of idea. We want to know, where is this function decreasing? Well, if my function is decreasing, then I know the derivative, or f prime of x, we're looking where that derivative is negative or below the x-axis. F prime at x, let's see, that's going to be 8x cubed plus 8x, and then let's set this equal to 0, and it looks like we can take out a common factor of 8x, and let's see what's left over. It's going to be x squared and then a plus 1, and let's go ahead and set each part equal to 0, so I get x equals 0 if we set that equal to 0. Inside here, if I say x squared plus 1 equals 0, well, that means x squared has to equal negative 1, and that can't happen. So I see that this is a cubic function that only crosses the x-axis once. Well, that's pretty nice. Okay, so let's see. We're going to put our 0 in. Cubic function. So it's going to look something like this. And so we need to know for what values would my original function be decreasing. So for what values is my derivative negative? Well, from negative infinity, it looks like, up until 0. And again, that 0, I have issues with that being included. It can't be included. So for 12, it has to be C. All right, so again, we have the graph of the derivative. Graph of the derivative. I think this person that did these is on crack. Leave these open intervals. The AP exam won't look at that because they can't decide, but those should be open intervals. That's my decision on it, so let's leave those alone. So we want to know where's my original function decreasing if the derivative function looks like this. So f is decreasing when f prime is negative. So really, I'm just looking for the interval where we are below the x-axis. So all of this means f prime is negative and f is decreasing. So this area right here, so it looks like it's going to be, we're over the closed interval from -2 to 3. So it looks like we're going to be from 0 to 3. So number 13, your answer should be E. Right. So now number 14, oh no, it's a limit definition, isn't it? So let's see, what can we say about, then the graph of the function f at 2 is, notice we talk about increasing. Now concave, that's really a second derivative idea. Now stationary, that would mean that we're not changing. So we don't know what the function is, but we know that when we do the derivative and plug in -2, I get a positive value. So what this is saying is at -2 or at f prime of -2, we get 2.637. That's what they're saying. Well, if the derivative is positive at this particular value, we can say, well, positive derivative means the original function is increasing. So it's just another way to look at that. All right, now for the graph. Now with this is a very common question. You will see this. You're given the graph of the derivative and you're asked for the graph, which of the following could be the graph of f. So let's look at some major characteristics that we have here. Well, if we notice that we have some horizontal tangents, because notice right here where we have x-intercepts here and here, well, that's telling me at those points f prime of x is equal to 0. So that tells me somewhere through here I have some turns. And notice we can talk about relative mins and maxes also. So let's look at this. So my derivative went from a negative to a positive. So in this area, in this particular region around this point, then I should have, well, if the derivative went from negative to positive, then my particular function had to go from decreasing to increasing. And then over on this other side, notice we go from positive to a negative, which means I've got to have increasing to decreasing. So I got to have something like that. So let's look and see, well, do I have any of those functions that might have something like that? Well, answer choice A doesn't. Answer choice A is linear. So I don't think, and this was the derivative of g, so I don't think the original would have had to have been a cubic of some sort. So it can't be A. Well, let's look at B. Well, B kind of looks like that might be the right area, doesn't it? We have here where we would be negative to positive, so this function, notice, is decreasing and then changes to increasing, and then over here increasing to decreasing. So I would think answer choice B would be the correct idea. Now, if you choose D, then you have the idea of relative mins and max flipped. So be careful with this. All right, let's talk about the last one. And again, it's another graph. A little strange graph here going on, and we have the graph of a derivative. And so let's see if we can do some investigating about this derivative. So it looks like with the original function, we have an x-intercept here. So I know f prime at x equals 0 there. And notice we went from positive to negative. So that meant that f of x around that 0, around that area, went from increasing to decreasing at that point. So we have something strange going on, because it's not necessarily over here on the original going across the x-axis. It just meant we had some kind of hump going on there. So we've got something there. All right, notice I don't really cross the x-axis anywhere else over here, so my graph really doesn't have any more relative mins or maxes. So having that, knowing that information, well, let's look. What could we choose here? Well, I would have had a lot more x-intercepts, because that's x-intercepts, so can't be A. D, I don't see anywhere I could really say that I even had a horizontal tangent anywhere, so I don't think it's D. And the same is true with B. I don't see. So it's either going to be D or E, and the difference is a relative min or max. And notice we went from positive to negative, so that point right there should be a relative max. C is a relative min, so my answer is E.